Hello, in this video we're going to talk about the idea of limits and then its relation with continuity. In some textbooks, when they start talking about functions and they want to discuss single variable functions, they start with the idea of limits and they talk about what the limit is with epsilon delta definition, and then they relate it to continuity. What I decided to do was a different approach, which was starting with the idea of sequences and talk about limit of sequences because that's more approachable, and then relate that with continuity and eventually get it to the idea of limits. So first, what is the definition of limit? In order to be able to define the limit of a function at a point, what we need is the idea of being able to approach a point. So the idea is, if you have a function and you want to find the limit of f of x when x approaches x naught, you want to be able to approach x naught. So in other words, you need to have points in the set, in the domain of this function, that in fact do get closer and closer to this point x naught. Let me draw an example with the green color at the bottom here. Consider this function. So this function, the domain of this function is from negative infinity to this point. Let's say this point is 1, and let's say this point is 2, and from 2 to infinity, union with x naught, and x naught, let's just say x naught is 1.5. In the domain of this function, which includes things less than or equal to 1, greater than or equal to 2, and the number 1.5. In the domain of this function, there are no points close to 1.5 except for 1.5 itself, which means I cannot really approach the point 1.5. So it doesn't really make sense to talk about the limit of f of x when x approaches 1.5. But look at the contrast between this one example and the one up here. So if you look at this function, the domain of this function is all the numbers less than x naught. Of course, we can approach x naught from the left. We cannot approach it from the right, but we can approach it from the left, which is why we can talk about the limit of this function when x approaches x naught. So before we can even get to the idea of limits, we need to talk about the concept of a limit point. So here's the definition. We say a real number x naught is a limit point of a set D if there is a sequence xn in D minus x naught. So there's a sequence inside the domain excluding x naught that converges to x naught. So here is an example of limit points. 0 and 1 are limit points of the interval 0 to 1. In other words, there is a sequence inside the interval 0 to 1 that approaches 0, and there's also a sequence that approaches 1. So of course we know the sequence 1 over n approaches to 0. However, 1 over 1 is not in that set, so we're going to consider this sequence 1 over 2n that approaches 0, and 1 over 2n is inside 0, 1. Now we're going to consider 1 minus 1 over 2n. That approaches 1 minus 0, which is 1, and 1 minus 1 over 2n is also in the same set. Therefore, thus 0 and 1 are in fact limit points. Of the open interval. So that completes the solution for example 4.48. Okay, now that we know what a limit point is and what does it mean to be able to approach a point, we're going to get to the definition of limit. So this definition is going to be long, but the main idea is when we say f of x approaches a number L, whenever this happens, if xn approaches x naught, then f of xn approaches L. So this is what it means for the limit to be L. Okay, so here's now the formal definition. And it's long because we have to consider a lot of different possibilities. I'm talking about infinite limits, limit at infinity. There are like many different possibilities. So assume f from d to r is a function and L is a real number and x naught is a limit point of d. So the key here is x naught must be a limit point. Otherwise, we cannot really talk about the limit of f of x as x approaches x naught. We say f of x approaches L as x approaches x naught if whenever xn is a sequence in D, but we have to exclude x naught, because when we say approaching x naught, we aren't really talking about x naught that converges to x naught. The sequence f of xn converges to L. We say, so this is the definition. So anytime you want to show limit is equal to a number, you need to show x naught is a limit point, and you need to start with a sequence in D minus x naught and then show that f of that sequence approaches L. Okay, so that's the definition. Now, there are other possibilities. For example, if you want to define limit of f of x as x approaches x naught equals infinity, what you need to show is that if you have a sequence in D, excluding x naught again, that approaches x naught, then f of xn approaches infinity. So same idea, except that L is replaced with infinity. If you want to define what is the limit when x approaches infinity, you need your D to be unbounded. So if D is unbounded above, then we say limit of f of x as x approaches infinity is equal to L if whenever xn is a sequence in D that diverges to infinity, the sequence f of xn converges to L. So again, it's the same idea. Similarly, you can define f of x approaches negative infinity as x approaches x naught, or you can take many different possibilities. So you have these are the possibilities. X could approach x naught, x could approach infinity, or x could approach negative infinity. The limit could be L, it could be infinity, or it could be negative infinity. There are three possibilities here, so there are 9 possible combinations of limits. And as you see, we do have 9 of them. So the first one was limits. This one is the first one, this is the second one, this is the third one, 4, 5, 6, 7, 8, and 9 different possibility. But the idea is very similar. Okay, so let's now go ahead and look at a couple of remarks. But before that, if there is no real number L, or infinity and negative infinity also do not work for these, then we say the limit does not exist. So we say the limit doesn't exist if such a real number L does not exist, and also the limit is not plus minus infinity. If the limit is not a real number and the limit is not plus minus infinity, we say the limit does not exist. And in each case, when the limit is a real number, we say it's convergent. We say the function converges. And if the limit either does not exist or the limit is plus or minus infinity, we say it diverges. Okay, so let's now look at some of the relations between this idea of limit and continuity. Okay, so assume x naught is a limit point of D and x naught is in D. Then f from D to R is continuous if and only if a limit of f of x as x approaches x naught is equal to f of xn. The idea of the proof is basically it follows from the definition of continuity. Because what does the definition of continuity tell us? It tells us xn approaches x naught implies f of xn approaches f of x naught, and that's nearly identical to the idea, the definition of limit. The only difference is here xn is in D, for the other one is xn is in D minus x naught. But if xn is in xn is equal to x naught, then f of xn would be equal to f of x naught. So that is not going to cause any issues. So that's pretty easy to check. Okay, and the second remark 4.2, is that if you have two functions that are the same functions, then their limits are also going to be the same. So these two functions could be anywhere, anything at f of x naught. So let me first draw a diagram, and then we will go over the details of what the theorem tells us. So here are two functions. So here's one function, and here's the point. Let's say the point is 2, and here's the second function. At 2, the value is here, and the value is like this here. There's a hole here, and like this here. So these two functions are the same functions near 2. So in other words, there is some interval here, 2 plus epsilon and 2 minus epsilon, that over this interval the two functions are the same. Let's say the function, the blue one is f, the green one is g. F and g are the same over the interval from 2 minus epsilon to 2 plus epsilon, except for the point 2. So you expect the limits to be the same, because really what matters is not what happens far away from 2. What matters is what happens close to 2. Nothing else really matters. Okay, so suppose f and g are two functions. X naught is a limit point of the domain. If there is some epsilon positive for which f of x and g of x are the same for all x inside D intersection with x naught minus epsilon, comma x naught plus epsilon. So that's the interval from 2 minus epsilon to 2 plus epsilon, excluding x naught. So we do not include x naught because, again, the value of the function at that point doesn't matter. Then the limits are the same, provided that limit of one of them exists. Okay, and the proof is like very simple, because if you take a function x, if you take a sequence xn approaching x naught, then so if you take a sequence xn approaching x naught, then f of xn and g of xn are the same for large n, which is why their limits are the same. Okay, so this brings me to the next example. So again, just to recap, in remark 4.1, we noted that continuity is the same as limit equals the functional value. And in remark 4.2, we noted that limit is the same for two functions as long as the two functions are the same over some interval containing the given point, except at that given point. Okay, so let's look at an example. If you look at this function, square root of x squared plus 1 over x plus 1, the limit when x approaches 3, we are told that this is equal to 5 over 2. Although this would have to be, yeah, it's 5 over 2. Yeah, that's right. So here, why is that true? So in single variable calculus, you have learned that you could just plug in the value. If you plug in the value, you get 9 plus 1 over 3 plus 1 square rooted, which is the square root of 10 over 4, which is 5 over 2. So why is that true? Why can we plug in the value? And the reason is exactly what we have in this Remark 4.1 tells you that if your function is continuous, then all you need to do in order to find the limit is to plug in the value, sometimes called substitution principle. Okay, so we're going to go ahead and show that this function is continuous. X squared plus 1 over x plus 1 is continuous. And why is that continuous? Because it's a rational function. And then its square root is also continuous because the square root of x is continuous, something we proved earlier. So, since x squared plus 1 over x plus 1 is a rational function, it is continuous on all real numbers except for -1. Also note that square root of x is continuous on the interval 0 to infinity. This is also shown before. We have shown that this is continuous. Thus, square root of x squared plus 1 over x plus 1 is continuous whenever x squared plus 1 over x plus 1 is greater than or equal to 0. So whenever x squared plus 1 over x plus 1 is inside the domain of square root of x, that function is continuous. So x squared plus 1 over x plus 1 is greater than or equal to 0 if and only if x plus 1 is positive. And that happens if and only if x is greater than -1. So that means square root of x squared plus 1 over x plus 1 is continuous. So really, the point that I need continuity for is at 3, because they are talking about limit when x approaches 3. But I also know that it is continuous from -1 to infinity. Now, if you look at the point 3 is in fact inside that interval, and it is a limit point. So I can use remark 4.1. Note that 3 is a limit point of -1 infinity. For example, 3 minus 1 over n approaches 3. Thus, by remark 4.1, I can say the limit as x approaches 3 of square root of x squared plus 1 over x plus 1 is equal to square root of 9 plus 1 over 3 plus 1, which is root 5 over 2. So what we need to check is the function is continuous at that point, and that point is a limit point of the domain. Then we are allowed to substitute. Okay, so next we are going to go over a similar limit of x squared minus 4 over x minus 2. Of course, this one is not continuous at x equals 2, so we cannot just plug in the value. So note that x squared minus 4 over x minus 2 is x minus 2 times x plus 2 over x minus 2, which is x plus 2. This equality happens for all x except for 2. Also, note that x plus 2 is continuous at x equals 2. So and also we know that 2 it's continuous actually, in fact, over the entire real line. and 2 is a limit point of R. So for example, 2 minus 1 over n approaches 2. Thus by remark 1, I guess I called it, like, what was it, 4.1, the limit of x plus 2 as x approaches 2 becomes 2 plus 2, which is 4. So the limit is 4. Now the limit of the right side is 4 of this equality. The limit of the right side is 4, therefore the limit of the left side must also be 4 because of the other remark. So by remark 4.2, limit of x squared minus 4 over x minus 2 when x approaches 2 is equal to 4. And that's exactly what we wanted to prove. Okay, so we are done with this example. So we did two examples. One used remark 4.1, the other one also used remark 4.2. Now, a few theorems which are again quite intuitive by what you have learned from in single variable calculus, and these are: assume f and g are two functions and limit of f is equal to a and limit of g is equal to b, then the limit of sum is sum of limits, limit of product is product of limits, limit of ratio is ratio of limits if the denominators are all non-zero. And here a and b are real numbers. How do we prove this? This is pretty much follows from what we have done for sequences. So you take a sequence xn. I'm going to actually prove one of these just so you see how it can be proved. So let xn be a sequence in d minus x naught such that xn approaches x naught. By definition of limit f of xn approaches a and f of g of xn approaches b, because limit of f of x is equal to a and limit of g of x is equal to b. Therefore f of xn approaches a and f of xn approaches b. Thus f plus g of xn, which is f of xn plus g of xn, approaches a plus b. And therefore, so I showed that f plus g of xn approaches a plus b. That tells us that f plus g as x approaches x naught is in fact a plus b. So this completes the proof for part A. And the proof for part B and C are nearly identical. So we are using properties of limit for sequences. Okay, so next we're going to talk about theorem 4.11, which is about the composition of two functions. So what happens if you want to find the limit of composition of two functions? Suppose d and u are two subsets of R. Let x naught be a limit point of d. So we have a set d, and x naught is a limit point of that. It could be inside x naught or it could be somewhere in on its boundary. Why not be a limit point of u? So here's the set u, and we have a point y naught that is the limit point of u. F goes from d to r and g goes from u to r. However, what I also know is that f of d minus x naught goes into u minus y naught. And the reason I need that assumption is that I need to be able to look at the composition, GOF. This composition is the key for being able to this condition is the key for us to be able to talk about composition of the two functions. We need image of the first function to be inside the domain of the second function. If that were to be the case, then the limit of g of f of x would be L. So f of x approaches y naught and g of y approaches L. Then when you compose them, you are able to get to L. So let's say this is the limit L. So you're able to conclude that g of f of x is in fact L. So it's not very difficult to see why that theorem is true, and I'm going to actually prove this theorem. If you want to show g of f of x is L, first note that x naught is a limit point of the domain. So x naught is a limit point of d minus x naught. So I can take a sequence, let xn be a sequence with xn converging to x naught. Now, since limit of f of x as x approaches x naught is equal to y naught, that was one of the assumptions. We have f of xn approaches y naught. So the sequence f of xn approaches f of y naught. Now note that f of xn is inside u excluding y naught, because that's what was given, since f of d minus x naught is inside u minus y naught. That was one of the assumptions. Okay, so f of xn is in there, and f of xn approaches y naught. Since g of, so let's see what the assumption was. G of y approaches L, as y approaches y naught is equal to L. Limit of g of f of xn as n approaches infinity. So combine this condition that we obtained, f of xn approaches x naught, and this one approaches y naught. So if I replace y by this sequence, because that sequence approaches y naught and is inside u minus y naught, then this approaches L, and that means limit of GOF of xn is L as n approaches infinity. So what we showed is that if you take a sequence inside the domain of GOF excluding x naught, then GOF of that sequence approaches L. So by definition, limit of GOF of x is exactly L as x approaches x naught. And that completes the proof. Okay, so let's go ahead and look at an example. Okay, so we have a function f that approaches 3 as I'm sorry, it's a continuous function. So they told us that it's a continuous function, and it f of 1 is equal to 3. So that does tell us that limit of f of x as x approaches 1 is in fact equal to 3 by remark that we talked about, 4.1, because it's a continuous function. So now if you look at the function here, x squared plus 1, x squared plus 1 is also a continuous function at 0, since x squared plus 1 is continuous on R. Limit of x squared plus 1 as x approaches 0 is equal to 1. I can just plug it in by the same remark again, by remark 4.1. Okay, now that I know the inside approaches 1, I can use the composition property. The only thing that I need to check is that if I call it, if I call the inside g of x, I also need to show that g of x, the domain is sent to, so if I take g of r minus 0, that is sent to, so if I take g of r minus 0, that's sent to r minus 1. And this is because if I plug in 0 here, I get 1. But if I plug in something other than 0, I get something other than 1. So therefore, I can apply the theorem above by theorem. And this is the theorem that talks about composition, 4.15. Limit of f of x squared plus 1 as x approaches 0 is in fact 3, because the inside approaches 1, this does approach 1, f of that would approach 3. And that's the end of the proof for this example. Okay, so let's go ahead and do the last theorem, called the Squeeze Theorem, and that would be the end of the video. Okay, so the Squeeze Theorem. Suppose we have three functions, f, g, and h, and x0 is a limit point of D, for which g of x and h of x squeeze f of x. What does that mean? It means f of x is in between g of x and h of x. G of x approaches some number L, and h of x also approaches the same number L. Then f of x must also approach the number L. Okay, so how do we prove this? The idea would be basically the same thing as we have done before, which is you start with a sequence. You start with the sequence xn, and you allow the sequence xn to approach to L, and then you show that f of xn must approach L. So I'm gonna write down the sketch of proof. So let xn be a sequence in D minus x0 with xn approaching x0. So I would like to show that f of xn minus L is small. So I'm gonna write down I'm gonna write down absolute value. So what I need is f of xn minus L. I want to show this is small. So absolute value of this is going to be so I guess I'm gonna write it down as h of xn minus L and g of xn minus L. So I have that. Now, if you look at the absolute value of this number, absolute value of f of xn minus L, this is going to be less than, since it's between these two numbers, it's less than absolute value of one of them. So it's less than maximum of the two absolute values, h of xn minus L and g of xn minus L, by properties of inequality. And you could say this is less than the sum. And if you notice that, then you're basically done, because you can make this one at some point this is less than epsilon, at some point this is also less than epsilon. So if you make both of them less than epsilon over 2, then you can make this one less than epsilon. And this tells you that f of xn approaches L. And once you know f of xn approaches L for every sequence xn, then you know that limit of f of x as x approaches x naught is in fact L. So this brings me to the end of the video. So next time we're gonna in fact talk about differentiation. So if you would like to continue along with this course in advanced calculus, feel free to subscribe, and I will see you in the next video.